Hello, functional programmers. The next thing I wanted to say was usually I play a song that has something to do vaguely with the title of the presentation. That was Somewhere Only We Know, and that was and that one didn't because it was an exception to that rule. So anyways, the other thing I have to tell you is that we have these feedback forms that people put on Piazza. In particular, these mid-semester feedback forms are for the course as a whole and the TAs. You were given 5 minutes in lab to fill this out explicitly, and not all of you did. In fact, not even half of you did. So please do fill this out. Okay, if you're upset at me for my polls, okay, don't take it out on the TAs, because this is the only time that TAs get feedback. So they really want to hear from you, and they're really excited to. So please, please, please take the 2 minutes or however long it is to fill this out, because it will not take very much of your time, and it will make the day of the TAs who have been working on this for almost 6 weeks at this point, okay? Or it won't make their day, depending on what you say about them. But don't say mean things, okay? Cool. Okay. Yes, and I think that's the last thing I wanted to say. Okay, cool. So today we're talking about exceptions. If you thought the last lecture was hard, then you're going to think this one is not hard, because it's not. We went up in difficulty all the way, and now we're going way down. This one's chill by my reckoning, okay? But still new content, all right? Some of you are not happy about the last lecture, and that's okay. But something I have to tell you is, if you were confused, please, 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 again, I will say this again and again until I have to at the end of time. Look at the slides after the fact if you were confused over the previous lecture. I've very carefully structured it so that if you read it, like, you should be able to get the same content out roughly, okay? And they're structured in a way that you should be able to follow along. So if you read them and you still don't understand, come see me or read it again, okay? But before starting the homework, I highly recommend you get the concepts down, okay? Cool. All right. That's my 3-minute diatribe. We're going to go ahead and get started with exceptions then. This image is also AI generated. I like it a lot. And you'll see why I chose this in a bit. So Menti code as usual. All right. So on our docket, we've got exceptions, we've got using exceptions, custom exceptions, and then this thing I'm going to introduce called exceptional control flow. Previously, we had continuation passing style. Now we're going to have something called exception handling style. Right? But we're going to see that in a second here. Okay. But moving on, last time we learned about the CPS thing, which is kind of, the motivation was sort of, let's make tail recursive functions automatically. Okay, the compiler can do this. And that's not quite the right motivation in terms of, like, you don't really care about that. The first motivation is that it's really good practice. It's really, really good synthesis of everything you've learned this entire semester. 2 is that it makes control flow explicit. It's interesting to see different ways that you can structure control flow. And what I mean by that is a different way of doing instructions in SML than just go compute a value and then come back to me. Continuations are kind of a disruption to that idea, or a refinement on that idea. So what we're doing today is going to be the same deal, where we're kind of treating control flow differently and seeing how control flow can be different. And then the next thing, well, this is just recapping CPS, so I don't really care about that for this lecture, okay? All right, exceptions. What are exceptions? Well, I think you already know the answer to that. Remember the definitions for the behaviors of an expression. What are they? Shout them out to me. Value. Evaluates to a value, right? What's 2? Loops forever. Thank you for saying it, because this is exactly the order I wanted it in. And then what's the last one? Raises exception. And raises exception is in Times New Roman Calibri 12.5. Because today we're talking about raising exceptions primarily, okay? This third behavior that we haven't really talked about a whole bunch, but today we'll give more detail, okay? I've been intentionally not telling you about it, but now is the time to peel back the curtain, which is the theme in this course, okay? Recall the expression 1 div 0. What does that expression do? Please tell me. What do you think? It loops forever? No, it does not. If you type 1 div 0 into the SMLNJ top level, what you're going to get is the uncaught exception div, which is a kind of explosion conceptually, but it's not exactly an explosion, okay? Because you divide by 0, and that wasn't a great thing to do. So that's one example of an exception we've seen so far. But we're going to see some other examples that are also reasonably interesting, because these exceptions are actually not special. They're very common to a lot of things at the NJ top level, including div, including mod, and there are a few more that are a little bit more fundamental to how we use SML. Okay, and I put my chalk somewhere and I can't remember where. Whoa. Okay, well, it'll turn up. Oh, here it is. All right. So div is specific to a certain function, the division and modulus operators respectively. But here's two more for you, okay? And you may or may not be familiar with these. One is the exception match. Match is an exception that is raised on a certain circumstance, and the other one is called bind, okay? Match you get when you try to use a non-exhaustive match, or you enter a non-exhaustive match, and then, or a non-exhaustive match that, the case of a non-exhaustive match that you didn't take care of. And then bind is raised when you try to bind to a value something that doesn't match. So I'll show you an example of that, okay? So if I'm just going to do the board from now on. If I do this, so I define f to be a lambda expression that does this, right? The NJ top level will yell at you, hey, that was a non-exhaustive match, right? Because why? What's wrong with this function? What am I not taking care of? Any case other than one. Anything that's not that will not be matched properly. So, whoops, that was a really bad one. You have to be careful when you're defining these functions. So if I did fn 1 goes to 2, boom, match non-exhaustive. And in particular, if I bind it, fn 1 goes to 2, what's going to happen if I do this? Boom. Uncaught exception match. Oh boy, you didn't match properly. The match was non-exhaustive. So you got an exception, but it says uncaught, okay? Which signals you might be able to do stuff with that later. The second example for bind is, right up here. If you try to do, so an archaic way of doing tests is that we used to do something like this. We would say val, like 1 equals something, okay? Some expression, and then it would try to bind to this thing on the left-hand side. And if it pattern matches, then it binds. Then it matches, rather. And if not, then you get an error, right? Which is this. So, boom, we have another bind, which is, or another exception bind, because 1 plus 1 evaluates to 2, which does not match 1. So therefore, there's no way that this pattern matching can match. Yes. Yep. I shouldn't say bind, I say match, because this does not produce a binding. This pattern does not have any variables in it. Therefore, it does not produce any bindings. I would say that I tried to match 1 to 1, and then I succeeded with 0 bindings. On a conceptual level, this is kind of the difference between some, or none, and then some of nil, if that makes sense. But this doesn't really matter. Okay. But yes, these are two examples. One way you can think about it is that if I define fn 1 goes to 2, this is kind of implicitly a function which says this. Any other case goes to raise match. So this is a useful way to think about how this is kind of desugared. If you ever specify something that isn't matched, it's just going to go to a wildcard that raises match. Okay, and that's one way to think about it. Okay, so this is everything that we just saw. Okay, and these two exceptions are the most pertinent to using SML in general, okay? Because they're the ones that arise out of just doing common processes like binding and matching, okay? But there are more specific ones for certain functions like the div exception itself, okay? All right, so what else can we do with these exceptions? Well, yeah, I basically just wanted to say that if I don't return a value, if I can't return a value in certain cases, I might want to raise an exception because sometimes it's not defined when I need to return. Div is a partial function, but I don't want it to loop forever, and I sure don't want to give back a value for dividing by 0. So what I'm going to do is exceptions. The whole point of having exceptions is that I can provide a convenient escape hatch so I don't have to give you an answer. Okay? It's like if you asked me a question in lecture, and then I said, raise div, and then I went on to the next topic. I just completely aborted. All right? But if you've been paying attention, remember that we learned about these things called options, right? We learned about options, which are sum of x or none. And this is itself a way of returning an optional value, right? Of giving back no answer. Because any function that's marked as a t option returning, then it must give me back something or it gives me back nothing. And it seems like a better way. In fact, I will say it is a better way of dealing with this because it's a type level distinction, right? Let's look at the type of div, right? Div is of type int star int to int. Now, looking at this divide function, right? as a human, as a SML programmer, like 6 weeks in, you know that div can raise an exception. But if I gave you this information, if I told you div is of type int star int to int, you would have no idea that it could possibly raise an exception. Because why? It's not in the type. It's not in the name. Nothing about this divide function, other than the fact that you know it's the divide function, should have told you that it raises an exception. That is really bad, because exceptions are really bad, because you need to be careful about when you're using them. Because you're running your long-running proxy server, and then suddenly you enter a corner case you weren't accounting for, an exception gets raised, and then you get a 0 on 213. All right, that's what happens. Don't do that. All right, so we got to come up with a better way of dealing with this. I don't know if my sequencing is right. Oh yes, so man, I already spilled the beans. Let's go ahead and talk through it. We can define a new safe div function that has this type signature instead. All right, so safe div will be of type int star int to, someone tell me what it returns. Int option, right? Which is a much better type signature, because now I look at this and I say, oh, it's an option. Huh, didn't think of that. And now I see that if I ever divide by 0, I get none, and otherwise I get some, right? And that's exactly what I wanted. All right, now it's safe, and now if I'm using safe div, I cannot do something like, I cannot proceed to do something like, oh, let me do one safe div, or capital safe div x, and then add that to 2, right? I can't just like go on my merry way and then add this. Why? Because this is an optional value. And the only, as you learned when we did sublist sum, the only thing you can do with an optional value is you case on it. And then in this case, I would I would do something for the none case, and then in the sum case, I would go ahead and like add 2 or whatever I'm doing, okay? But you shift the burden of dealing with this to the caller versus the burden being, well, sometimes your stuff gets wrecked, right? That's kind of like the promise of an exception raising function. So this then begs the question, like, okay, all right, that's cool. Why are we even using exceptions at all? Why even have exceptions when I do have these very nice optional values? And the answer is that sometimes it's a pain, all right? We're programmers. We are lazy, all right? A non-negligible amount of my motivation every day is producing as few lines of code as possible in a given day, okay? I'm trying to do my best. So let's look at these two specifications. Here's another note I wanted to say. If you look at the full specification, right now on our div function, we had this requires n is greater than 0, right? We had a precondition, or n is not equal to 0, sorry. N is not equal to 0, and then otherwise we're going to get what we wanted, right? We put that in the requires, the precondition. But for safe div, we have none. Yes? D is not equal to 0. Yes, thank you. D is not equal to 0. That's a good point. But for safe div, we have absolutely none because of the fact that, well, why? Because I moved it to the type. So again, with this parse don't validate stuff I was telling you about in lecture 4, that comes back where it's like this dichotomy, this tenuous connection between specification between preconditions and types, right? We just moved the burden to the type itself, okay? And that's a better way of doing things usually, not for today's lecture, right? Cool. Blah, 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 I already said this, okay. But this might be a little bit of a burden. So here's what I'm going to say to you. Suppose that I wanted to compute people's grades and then find the average, which is an example I actually already used on you last lecture. So we're going to call it average grade. And this is for like a particular student, okay, let's say. So we have L, which is of type int list. So let's suppose I have everyone, this particular student's like grade on every assignment, and I want to compute the average. What would I do? What's a handy way I can do this without having to define my sum function? Fold? List.fold L or list.fold R? Doesn't matter. Good point. Fold L, up plus 0, our good friend, and then I give it L, parens, div, list.length, or just length. I think it's also available at the top level. L. Fair enough? This is my average grade function. But then, well, how much faith do you have in me? Because if my bookkeeping is correct, this is cool. But if my bookkeeping is not correct, and for some reason my grade spreadsheet is empty for a particular student, that means that my grade calculating program is now going to crash. And suppose I'm in the middle of calculating your grades for the mid-semester, and it's like 11:59 because I procrastinate, and then the registrar needs the grades in the next minute, and then it crashes. Why? Because I used this div, all right? Wasn't great. This is actually the opposite motivation, which is I'm telling you that I want to use the safe div. So if I wanted to be rid of exceptions, I'd say this, right? And now it returns an option. And now I can go handle that wherever. And I can, like, if I happen to get a none, I'm like, okay, I skip maybe. I skip the student rather than aborting execution entirely. Those are two options. I can skip the student, or I can not calculate grades for anyone in the class. Okay, those are, it's not a great binary, right? Except that's kind of stupid, I wager to you. If you have some measure of trust in me, you should be able to ensure to think that, you know, maybe my grade spreadsheet is not empty, because that's kind of a silly case. So having to handle this extra logic here, like when I go and use average grade, when I do my case average grade of like this kind of thing is kind of painful when I have a fairly good precondition. Like I as myself, I kind of trust, yeah, my grade spreadsheet is not empty, because even if it was, I'll just put it back in and then be good for the next time I ran the program, right? Like it's not really going to take me a very long time to compute people's grades. So in this case, what I'm trying to say is that it's kind of silly, because we have to acknowledge the failure case, and we have to sometimes, at a certain point, trust our preconditions, okay? I know this whole time I've kind of been telling you preconditions suck. I hate preconditions, but also preconditions are great because they're better than nothing at all. So at a certain point, you do have to go to the precondition, and I'm willing to bet that I didn't screw up and that my grade spreadsheet is not empty, okay? So in that case, I will be okay with this, right? So in this case, I'm going to say, okay, because I know myself, because I know that I am in a hypothetically impossible case, I'm all right with the exceptional behavior. This is exactly what has caused 1,000,000,001 bugs in real life code, okay? So I want you to be careful with this line of thinking. The line of thinking of, oh, I trust myself. Oh, I know what I'm doing. Oh, I would never have happened that. Oh, that's impossible. All right, raise your hand if you ever written code, said that was impossible, and then it happened. Yeah, all of you should be raising your hands right now, okay? I don't believe you if you're not, okay? Like, trust yourself. Don't get me wrong, but like, lesson of the day, don't trust yourself too much, okay? So what I'm trying to say is that, yes, we can use exceptions, but be judicious. Be aware, be safe. And this stretches beyond like this homework, okay? I'm saying for the exceptions homework, for what you're doing in this next homework, please do use exceptions, because that's the point. But in your real life code, when you go off and like become a software engineer or whatever, remember what I said, and don't use exceptions if you can help it. All right. I'm contractually obliged to teach you this material, but I'm not trying to encourage it. Okay. Cool. Just checking. Okay. And the trade-off seems really bad, right? Because it's kind of like, oh, I can, you know, risk my writing 2 extra lines of code for something that might just crash my program. And if I have a really long-running program, it might make it seem like doing the safe div is never worth it. It's never worth the amount of code golfing, except, as you can see on my slide, we do have a way of dealing with exceptions, which I've been trying not to acknowledge for the first few weeks, okay? We can handle exceptions. We can recover from a raised exception. We can rebuild, okay? All right. So part 2 of this lecture is going to be on how we can use exceptions in certain ways. So let's go through this, right? So SML, the most important thing to know here actually is there's a type called EXN, all right? Oh wow, I didn't realize this was on here. There's a type called EXN, and that in fact is the type of all of these things I just told you about, right? Match and bind and whatever. So this EXN type, you can think of it like this. Data type EXN equals div or match or bind. All right, this is kind of how you can think of it. It's a sum type, it's a variant, and then I'm going to put an asterisk here, and I'm going to come back to that, okay? But here are 3 valid constant constructors of type EXN. So that means, remember that because of this, we have that div has type EXN, match has type EXN, bind has type EXN, right? They're all of this type EXN, which you can think of as standing for exception name, but at this point, it might be lost to the annals of history. I'm not actually sure if that's true. But also, we have fail, of string. I'm sure you've seen this. I think it's on your homeworks, right? Fail unimplemented. So fail is actually not of that type because remember your data types. Fail must then be of type string to exn. Exn is not special in this case, right? It just looks like a regular data type declaration. So these are all certain exceptions that we have available to us, and we can say raise e to raise that exception. If I ever write raise and then e, which is of type exn, right? For e of type exn, then it will raise that exception, and then everything will get wrecked. Okay. So for instance, like we could do this ourselves. I don't know if you've done this, but if I wanted to, I could explicitly raise div. Now this would completely wreck my program, but I could. Ignore this. Like seriously, ignore it. It doesn't matter. And then I can also raise match. And I can raise bind, which means I can also define to you def fun function, which takes in an input and then it raises div. Oops, sorry. Whoops. Def fun function x. Oh wait. Frick. In my defense, for my job, I have to work in one of like 20 different languages at the top of a hat. The fact that I've made as few language-specific mistakes as I have is honestly impressive to myself. But I can make this function, fun function, and what does it do? Let's see what fun function does. Let's give it unit. Oh shoot, I got div. What happens if I give it one? Oh shoot, I got div. Yeah, this function just raises div, which might not seem super useful to you, and indeed, I don't really see why you would ever write that function. But there are other functions we can write by raising exceptions. Yes. Of raise, yes. So that's the next. I believe that's the next slide. But I'll say this anyways. So okay, let's get rid of this. Raise is not a function, is worth noting, okay? As in, you cannot do like val x equals raise. Any time you have raise, you have to have the argument. But raise e for e of type exn is of type alpha, and I'm going to also put a star here, but I'm not going to come back to it because there's a technical detail that might not make this 100% spiritually correct to say, but conceptually it's correct to say. All right, it has type alpha. That's all you need to know. This thing has type any type. Why? Because if I'm writing a function and I have an exceptional case I want to deal with, I don't want to. If this had like type int, now I have to like do a bunch of like cartwheels because my return type might not be int. The point is, if I say e is of type t, right? This like judgment, this like thing I say, this is only true if and only if e evaluates to a value, then v is of type t, right? The point of this kind of supposition is that it's predicting the future behavior of the code. But this might not be true. It's if it returns me a value, then it should be of that type. And raise never returns a value. Therefore, why not give it whatever type you like? We're not constrained to give it any particular type. So it has polymorphic type. And my comment about how raise is not a function, it means that it's not correct to say this. Like you couldn't do this, right? Which otherwise you might be able to think of it as like it's mapping, get the first thing and then apply raise to it, but you can't do that. Yeah. Yeah, they're values. Values, exceptions are values. Functions are values, exceptions are values. What isn't a value nowadays? We can make it spicier too. Div. I don't know why it prints like that. That's interesting. But fail high. Boom. All of these are values of type exn. Why not? The one thing you realize is like everything in SML, you can kind of de-sugar to like something else because this makes for a really nice thing where like nothing, very few times have I had to tell you something new outside of the first like 4 weeks. It's always been an application of something you've already seen or a natural consequence thereof, right? So that's just some trivia, and I'm only saying it because this is a relatively chill lecture, and knock on wood, there is no wood. I'm probably going to finish. Yeah, there's no, okay. Cool. All right, cool, okay, so I already said this, but yeah, it never returns. It's okay to give it whatever type I like, all right? Cool. Any questions on this? Any questions on exceptions thus far? Because this will get not actually that much more complicated, but it will get a little more complicated, okay? All right. So we also have a language construct called handle. All right, handle lets us handle exceptions, and the way that it works is we can write something like this. All right. I want you to put yourself in. Oh, and I shouldn't have. Now that I think about it, I shouldn't have erased it. But we're gonna go back to the average grade case. Okay. All right, we're gonna do average grade. But now we're going to report the grade. Like I want to get out a string that I can show to your parents about what your grade was, okay? So here's what we're going to do. I'm going to stop writing lists because it's annoying me. And we're going to use fold-r this time because I feel like it. Addition is commutative. Okay. No. Actually, I shouldn't have said that. Foreshadowing. Anyways, we're going to do div, and then we're going to do length of L, right? This is my thing. And then I want to say, well, let me, actually, sorry. AVG equals yeah, so I wanted to actually do something special. Your grade is, I didn't actually give you the student's name, so this is the best I can do. But I'm concat int.toString of AVG end, right? And this whole thing, I realized I kind of left the line there, but this whole thing is an expression. It's essentially equivalent. No, sorry, it's not. But it does the your grade string thing, right? It's essentially spiritually the same as before, except we know that this div might raise an exception depending on whether or not L is empty. So we're going to use our nice handle construct, and I'm going to tell you it'll look like this. I don't think I have to put parens here, but I will. Because remember, let is an expression. I say handle div goes to error no grade found. All right. What this means is handle takes in on the left here an expression, and it says if that expression ever raises an exception, pattern match it against a certain number of clauses of exceptions, of exception constructors. You see the value in having these exception constructors, which is that you can pattern match upon them when they're raised. Okay? So when this ever raises div, we will pattern match on it, and then if it matches here, which it does, we will enter error no grade found. So that means that, I think I give you some examples. Your grade is, the average was, oh, and also, I guess in this case, it was a string start int list. I don't care. Cool. I want to show you some use cases, but basically, I'll write it down on the board, right? So if I wanted to use this function, oh, shoot, did I just delete? Whatever. If I wanted to use this function, I might say average grade 1, 1, and this will evaluate to da 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 da. Your grade is, from there, 1. But if I wanted to do average grade on the empty list, what am I going to get? Error. I'm too lazy to write the rest. Okay. Yes. That's my average grade function. So we can recover from these things. Okay. And it's all because of the simple rule that this handle thing obeys. Okay. And let me write it out. I'm actually going to erase this because I want more vertical height. Okay. The general form which I'm going to write out, just so that we're clear on everything, is this. I've got some expression E. I handle it. And I give it some number of patterns. P sub 1 or dot 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 or sorry, P sub 1 arrow E sub 1 dot 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 or it's better write like this actually. P sub n arrow E sub n. Okay, this should look like a case. It looks very similar to a case. The same way we have like none goes to blah or sum of x goes to blah. After the of, we have that after the handle, right? And I'll corroborate up here. But another thing we have to have is that each of these expressions, has to have type T, where E has type T. That is to say that each handle case, each of these, has to have the same type as the thing I'm handling. Why? What is the reason for that? Well, like more specifically, I basically told you the typing rule. Like, I don't know. I feel like to say like so it's well typed is like I meant more motivationally. Like basically this breaks type safety. Okay, this means that we might get multiple types out because if E were not to be of the same type as E1, then suppose that it didn't raise exception. Then this expression would go to E of type int, let's say. If it did raise exception, we'd go to E1 of type string, let's say. Bad, no bueno. Don't do that. Right? Don't mix your types. So therefore, we want to make sure that all these things are of the same type. And each of these patterns, I know I haven't really said like patterns have types, but they kind of do. If you think about it, like a constant pattern 1 has type int. So like each of these patterns should have type exn. Okay, and that's kind of the idea. And then we can describe behavior with just these few clauses. If E never raises an exception, it's just E. The handle doesn't apply. The handle only matters if there is an exception. And if E raises an exception, then it will go and pattern match to each of these P sub I clauses in order, same as a case. But now it'll be not casing on the return value, it'll be casing on the raised exception, okay? We march on linearly, and then if it reaches one, the first one it reaches that matches, it will become that, okay? And then if it doesn't match any of them, then we re-raise the exception. We go back up to the next handler, okay? So let me give you a concrete example here, I think. Suppose I wanted to do one div 0 handle match goes to, I don't know, A. And then I want to handle that div goes to B. Does everyone see what I'm doing? So the handle applies to this entire one div 0, okay? I handle it for match and I go to A. Otherwise, I handle this whole thing to div and go to B. What do you think it's going to be? Oops, it's type error is what it is. Maybe it doesn't do that. Let me put two parens around this. Maybe I was wrong about the association. Oh, sorry, you're right. It's a. I was thinking. Let me do a nice example where it's returns a string, but actually I should do this. Sorry, you're right. Handle match goes to A. Handle div goes to B. Oh my god. Okay, I've uncut parentheses. All right, you know what? It doesn't matter. One div 0 handle match goes to 0, or handle div goes to 2. All right, there we go. I wanted to do like a nice all you can see is A or B and not 1 and 2, which are meaningless because there's so many of them. But geez, what can you do? Raise div, handle that. Does it match the match? No. So we re-raise. So this becomes raise div handle div, and then the div is raised and the handled by this guy. So then we match the div, and we get 2. Okay? Yeah. Only if this didn't raise an exception. If this thing didn't raise an exception, what happens is we get the int, we bind it, we go here, we get the string, and then that truly passes in. And then that goes into the handle, the string. And then because it wasn't raising an exception, then we proceed linearly. But this handle is surrounding this entire expression. The next component of this I was going to tell you is that exceptions propagate up. Exceptions, if I have a sub-expression which raises an exception, that means the whole expression raises that same expression. So this guy is a sub-expression of the greater let. But if this div in here ever raises a div, it'll go out to this, it'll go out to this, and then it'll go to the handle. If this were to raise an exception, yes. So only the right-hand side needs to be of the same type as the thing being handled. The thing being handled in this case, because it's a string concatenation, has type string. And then the thing I produce if I raise an exception is of type string. This one's well typed. Yeah. with the new. Oh, I see. Okay. Instead of that, what I'm going to do is, oh, geez. One div 0 handle div goes to, and then what I'm going to go to is now I'm going to say raise fail high, handle fail. I'm going to show you that you can actually bind that constructor. The thing I gave fail, you can actually bind when you handle it. Goes to s. Sorry, I should not do that. I should do. I want it to be well typed. Shit. Okay. Basically, I think that this is just a parens problem. So what I meant to say was, if indeed you handled match to go to 0, and then this guy was handled to say div go, oh, no, sorry. If this thing was handled to say div goes to this whole expression, right, associated, I think it would be fine, because this would be about type alpha, handle goes to int, but I think I just messed up the parens. And I do not have RL wrap on, which means I can't go left and right, which is so sad. But indeed, you could raise whatever exception here, like another exception, and then that handle would be specific to this. You have to be kind of careful, because actually it's ambiguous. Because if you don't put the parens, I could foresee this handle modifying just this, or I could see it modifying this. Or actually, no, I know what happened. I know what happened. We're gonna do this. It became this. Do you agree that this is nonsense? So what? This is a parsing thing. When you're doing handles, be very careful with your parens. Basically, what I'm saying is that this thing above, which was well ill-typed, was because I didn't expect that the parens would associate this way. The handle is modifying match, which is nonsense because match doesn't raise match. Match is match. Okay? Well, that's another good question, I guess, which is that div match, div handle div goes to match is going to still be div. Because this is div. It's not raising div, it is div. Okay? This gets kind of meta. But my point is, be careful with your parens. This would have worked had I put a left paren here and then kept the other thing the same. Okay. And if this is confusing, that's okay. You're going to go through plenty of fun trivia exception examples tomorrow in lab. This is so trivia. Any other questions about the trivia? We can play. I mean, yeah. I'm pretty sure in this case you can. I wanted to be safe though, and this is clear good reason for why you should be safe. So really, I'm teaching you by failing because, like, be careful. What can I say? Cool. All right. We're gonna move on. Maybe I should move a little. I don't have that much. Okay. So here's some other examples. If I do raise div, that raises div. If I do raise div handle div, goes to 2. That goes to 2, right? Because I handle it. Raise div handle bind just raises div because we match against this and we fail. Raise div handle bind goes to 1 or div goes to 2. Then we raise the div, we look at bind, we say nope, not the same. Then we go to div, we say oh yeah, that is the same, and we reduce to 2. And then 2 handle div goes to 3, goes to what? That should be 2. Sorry. But yeah, any questions on this kind of stuff? Yeah, it's a simple idea, but it composes with itself. You can make these arbitrarily complex. Okay. And then the other thing I wanted to tell you was that if a subexpression raises an exception, which I kind of alluded to, then the entire expression does. And I'm not going to write this out because it's kind of not interesting. But basically, exceptions propagate outwards, meaning that if I have a handle surrounding an arbitrary function call, that means that if the function call ever raises an exception, it will go to that handler, provided that there is no handler in between them. What I mean by that is if I have f of unit, let me be explicit about the parens, handle blah, 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 goes to, let's say, if this function f ever raises an exception, we will go here, okay? But not if the function f previously catches the exception first, okay? Exception handling happens when you reach the handle, and then optionally it might continue. But you only catch it when you reach the outermost handle, the nearest enclosing handle, okay? So for instance, I just wanted to show you this thing. So okay, this whole nested expression is like big, and pretend there are parens around this. But we know that 4 div 0 raises div, right? So 4 div 0 raises div, but this is a subexpression of this guy, so this thing also raises div. But this is a subexpression of this guy, so this also raises div. And then because this raises div, then we handle it, Because it's raised as div, then because there's a handle, we match to it, and then we get 5. Okay? So it goes outwards. All right? Think of that as it propagates outwards like that. Okay? Cool. So this is pretty useful because it lets us essentially jump in our reasoning to somewhere that's very far away, but somewhere we were previously. If I ever see a handle, then I know I might come back here at the drop of a hat if this guy ever chooses to raise an exception. In essence, raising an exception kind of lets you fail. It kind of lets you continue from your failure. It kind of lets you failure continuation. I'm going to stop being so blatant about it. Anyways, it's kind of like a failure continuation. You can think of it as. It's also kind of like a go-to, which is bad. Okay. And before we saw there was this kind of relationship. I signaled to you that we can have this relationship between returning an option and raising an exception. It turns out, actually, if I have this function f of type t1 to t2, which might raise an exception, I can always define to you f opt like this. F opt is such that it goes to sum of res if f of x reduces to a value, in that value, or it goes to none if f of x raises an exception, and otherwise it loops forever. Okay? But I can always do that for you. Anyone like to actually wager a guess as to how I'm going to define f opt? Well, what might I do with this specification? It's not obvious, so it's okay if you don't exactly know. All right. What we're going to do is, in intention, here's what I want to do. I want to call fx, and I want to handle anything. If I ever get an exception, I want to go to none, right? So I say, and this is allowed, right? This is a wildcard pattern. Wildcard pattern is a valid pattern, and it goes to none. But I claim there's a problem. This is not going to satisfy that specification. Here's why. It's not going to type check, actually. Or, I'm sorry, it is going to type check, but it's going to constrain our type. In fact, let me just write it for you, and let's see why. On f opt x equals fx handle underscore goes to none. Sorry. I'm going to make it polymorphic, and that's what I should have done anyways. F opt, or like, yeah, make opt fx equals fx handle underscore goes to none. Because I don't have the f function available to me, I just like made it an argument, which I can do. But note that this function f must be of type alpha to beta option. F has to return option. I said to you previously, f should be of type t1 to t2, any t1 and t2. Why? It's because if this thing doesn't raise an exception, we get the result of fx. But that type needs to be the same as this type, which is of type alpha option, right? So if this is of type alpha option, and then this expression we're handling is of type anything, beta, then beta must be alpha option, right? So we can train it. Here's what we should do. Indeed. That is f opt, to make an optional function from any f. And in fact, I could pass in the f as an argument. That would be strictly more powerful, rather than do it for a specific f. But we can always do this. So we can always go between. Okay? And you could do the reverse as well relatively easily. Okay? Cool. All right. And then check your understanding, except I already told you. Second thing I got to tell you. This sucks. This is terrible. This is awful. Never do this. Never do a handle that catches anything. I don't care if you never intend to use SML after this. If you're using Python, never accept E. Never accept all, okay? Like, if you handle every possible exception, okay, because this would handle any possible exception, there might be some exception you were not aware of that gets raised. Like you do some random crap like an integer overflow, all right? Which is really, really friggin' bad, because now you're going to not know and you're going to get none, all right? So it's better to, if I knew what exception f raised, I might say like specifically, like if it's div raising, let me handle div, okay? But if there's match or bind or whatever, and I don't want it to go all the way here, all right? I want to know about that in that case. Otherwise, I'm not going to know, okay? This is, again, like a common sense tips rather than strictly curriculum, but please don't do this, okay? It's a really bad idea. Okay. And I'm not going to write this out, but basically, I've got this fx function. I do int.toString on this x, and then I concatenate it with this string, and I handle div to say divided by 0, okay? Here's my question. Is this true? Is f given 1 div 0 going to be divided by 0? It's going to enter this handle case. No. Who said it? Why? You said eager evaluation? Yeah. Whoops. All right, you can keep that one. You can keep that one. Take two. Yeah, okay, close enough. Eager evaluation, meaning that, remember, prior to entering the body of f, I'm going to try to evaluate 1div0 before I go and meet this handle. The handle never happens because this f is just a big lambda that looks like this, right? The handle is inside of the definition of f, but it's not outside of this 1div0. So 1div0 is going to immediately raise an exception. So this is not true, okay? And I think I actually had a short example for you here. Yeah, so suppose I've got this function f. Basically, it just like does 1 plus its recursive result, and then at 0 it raises div, okay? Let's see what happens if I do sum of f of given 4, and I handle div to go to none, right? Okay, so if I expand the definition of f, I get this big case, and then I get 1 plus f of 4 minus 1. Otherwise, I go to the 3 case, I get 1 plus f of 2, and I get 1 plus f of 1, 1 plus f of 0. And now I get this whole thing, okay? 1 plus a bunch of things. I'm here, like outside of me is a bunch of this random stuff. And I get 1div0. What's going to happen? Well, remember, look at this. I wanted you to see the way that like this handle is still here. If I view programming as just like the text changing, this handle is still there. And it's a sub-expression. This is a sub-expression of that. Meaning that if I raise div, I'm going to go straight out to this none. Because div gets raised, div. Handled none. Okay? So just remember that the handles stay around. They're persistent. Okay? But you can kind of just think of this in terms of the text changing, right? And then last note for this section is exceptions are something we call a side effect, basically meaning that it's something that's not just computing a value, like reading from a file, printing the console, imperative stuff. Raising an exception is a side effect. So is looping forever. So this means that this can break some of our nice ideas, like I should be able to permute anything that binds wildcard. I should be able to like put it in an arbitrary order. Not true, because if I put this first, I raise bind, and if I put this first, I raise match. And those are two different outcomes. So I can't freely permute things. It means that mathematical thinking is harder. That's why we prefer to work with total functions, because now I can't arbitrarily rearrange these if I so feel like it. Okay. And then a fun little fact about that, which is I alluded to earlier, is that addition is not commutative anymore. In an exception-raising world, addition is not commutative, because if I have E1 as raise div plus raise bind, and this is true because raise gives back whatever type. This is a well-typed expression. This way, div is what's raised. But the other way, bind is what's raised. Okay? Addition is commutative for valuable expressions, but not for arbitrary expressions. And this is because our definition of extensional equivalence is that you're only equivalent if you raise the same exception. Okay? That is a hard criteria. All right? It doesn't really matter, but it's kind of fun to think about. And I have this like little joke, like programmatic thinking is sometimes not mathematical thinking. Sometimes. It usually is. Okay? But I thought that was fun. All right, quiz time. Get up. It's a new third. The points have been reset. Oh, you're all working from 10 points. You have this for the second half. In the second half. Anyways, we're going to be talking about a brand new car, if a car is also an exception. Okay? Because we can have these nice exceptions that we previously just talked about. We can think of this data type EXN in this way, but it's not actually strictly how it's defined, okay? And I'm going to give you a motivating example first about why that is, which is our old friend fact. So fun fact is 0 equals 1, but also fun fact, this thing loops forever on a negative input, right? That is also a relatively fun fact. But I don't really like that, right? Because it's quite difficult to tell if something is looping forever or if it's just taking a really long time. In fact, it's impossible to figure out via mechanical means. So we want to do better than a function which knowingly loops forever on an input, even through its precondition. Why? Because people mess up the preconditions, okay? Like you can write this library function and they say, requires n greater than 0. And then on your GitHub page, 2 months later, someone will write, hey, my function seems to be looping forever when I give it a negative input. And you're like, yes, because you broke the precondition. I'm not salty. Okay, so we want to raise an exception instead of looping forever. And it turns out that what we can do is we can define new exceptions. So I already told you all this. So for instance, actually, sorry, I was supposed to do this first. Let's rewrite this, okay? Instead of doing n times fact n minus 1, we're going to say if n is less than 0, then raise something. But pretend you forgot about the thing about custom exceptions, and then say we do this. Or say we raise bind. Else we do n times fact n minus 1. And now this function no longer loops forever on any input I claim to you. Okay? But the problem is this raises bind. You're going to get bind. It's not very descriptive if your factorial function gives you bind. Like what am I supposed to make of that? What does that tell me? Nothing, because bind is supposed to be for if you failed to bind to some argument. Realistically, no library function should ever raise this unless whoever implemented it did something wrong, right? So if you do this, it's not a good idea, right? So back to this idea of custom exceptions. Also another thing I wanted to say is we should change the type, we should change the name of this to this. Fact_exn. In OCaml, it is a common practice that library functions that are possibly exception raising are suffixed with _exn. I just wanted to let you know, like I think that's a really good practice. Okay, like again, exceptions are not evident in the type, but you do have the name. So I think it's a really good idea that like if you're going to be calling a function that potentially raises an exception on you, it should be clear from the name of the function. Okay. Again, this is kind of my lecture to give you like random tips that aren't strictly course content. But okay. And we could raise fail like negative number or fact got negative number, right? We could do that. But now if I want a pattern match on that, I have to write like, handle fail negative number, right? I have to like explicitly write out the message. And guess what? If I make a typo and I forget this R, now it's not going to match, right? So I want to do better than that. Let's do better by making a new exception, okay? And I don't remember if I put it on this side. Right, okay. Let's discharge that asterisk I told you about earlier, which is that you can think of it as being defined this way, but it's also not, because it's also defined like this. EXN is the only extensible type, okay? You might also think of EXN as standing for extensible type. I'm halfway sure that that's actually a joke that someone gassed the professor with, but the point is that it's called extensible because you can add constructors to it after the data type was declared. There are no other types like EXN in standard ML, okay? It's not special, except in this case it is special. That means that if I wanted to add a new constructor to the EXN type, it would be as simple as me saying exception E. And then somewhere in the back of SML's brain, it'll like remember that, oh, hey, there was an E here now. Now there is one, okay? And along with all of the other exceptions. There are a few I didn't tell you about, okay? But the point is that this declaration lets you make a new exception. And now, after the fact, I can handle E goes to da-da-da, okay? Worth noting that if this is not the name of an exception, it's going to be treated as a variable, which means it will be a wildcard case. So be careful about that. If you misspell this, you are in deep water, okay? But you can have custom exceptions, all right? And that's actually a really cool thing. But because now it means, what can I do? Instead of doing this, I'm going to say exception, and I'm going to have my own exception. I'm going to have my own private little exception that I use and that vendors of my function should be wary of. And instead of raising bind, I will raise this brand new exception fact, which is descriptive. It's descriptive, it's easy to pattern match upon, and now I don't have to rely on someone else's exception and then possibly get caught up in their handling logic. Because if this raised bind, but elsewhere in our code we had to handle bind and we hit it on accident, that wouldn't be good on us, okay? So don't mix and match your exceptions, okay? Right, okay. So this is our new definition as I just showed you on the board, okay? And then if I did this, for instance, so I did sum of fact exn given -1, and I handled fact to go to none, I would get none, okay? Because the exception will be raised from this, and then it propagates outwards to the handle, okay? Any questions on this? Cool. All right. We can also have define exceptions that take arguments. I can do exception error of string, and then suppose that like I then defined a function f that could raise that function error. I'm defining a higher order function for you here called run process. It takes in a what I call a thunk, which I'll talk about a little bit more in a few lectures. But it's a function that takes in the unit and returns a string. So this function could do anything. Could raise an exception, could loop forever, could evaluate to a value. But run process takes in that function and it transforms it into a safe function, because if this function specifically raises error, I will handle it and give you out this nice formatted error string, or I'll give you output and then whatever string it returned. Okay? So basically this is like more transparent that like I now have a function which returns me a string. And it just runs it and then looks at the output. Okay? Is that relatively clear? Basically, I just defined a new custom exception that this function might raise, and then now I can handle it. Same as anything else you saw. This is just a specific application. Okay. So if I did run process on unit goes to foo, I would get the string output : space foo, right? Because it would take this and then it would concatenate it here. What if I had fn unit goes to raise error of bad? Then run process on that function would give me error : bad, because we'd catch the error and then concatenate it here. Okay? This is like a reasonably common thing you might want to do. I think it looks pretty clean. Okay. Whoa, did I not tell you that? Did I not write down the thing? Oh, I wrote in a footnote, didn't I? Okay. I just want to say that some people say EXN stands for extensible, but I've never heard that actually confirmed. It might be a lie, but you know, it's a pretty good one. Cool. All right. Last thing we're going to talk about, which is exceptional control flow. I think that on the board in the Citadel Commons, somebody wrote something about exceptional control flow at some point. I don't know who it was. But we're going to talk about how we can do, instead of continuation passing style, something called exception handling style. Right? Okay. Okay, so the point of exceptions is that we can quickly escape from an error case, but also, if we really wanted to, we could weaponize it, because this gives us a kind of control flow ability where I can say, stop doing what you're doing, and go to the nearest handler. The key term here is go to, which kind of signals it's not a good idea. Okay, to be clear, I don't endorse anything in this section, but I'm contractually obliged to teach this to you. All right. So here's what we can do. I want to define a function called search EHS. Okay, takes in a predicate, takes in a tree, and returns to me an alpha. All right, and what it does is it raises a brand new exception called not bound if there's no element that satisfies P, or it returns the first element in its pre-order traversal that does. Okay, so it's kind of like option.val_of or whatever, in the sense that like if it doesn't find the thing, it doesn't return an option, it just raises an exception. But in this case, it's this not bound exception. And actually, I didn't actually define it, so purely for my sake of mind, I'm going to put it here. And then pretend that this is below that, because otherwise it would be invalid SML code. And we're in the business of writing correct code. Cool. All right, so now that I've defined that function, let's define the search EHS. Well, what did we have earlier? And I'm going to show you 3 implementations. Oh, wow, I just like straight up did it. Okay, I thought I showed you the CPS version first. Cool. So let's start from here and let's do it, right? If I get none, what should I do instead? I should raise, right? Raise not bound. And the name would be search EHS, but I don't care. Okay, and then instead of sum x, I would instead return x. So let me get rid of this. But here, search no longer returns me an option because I've defined it to be such. So I wouldn't do this, actually. I would erase this. But here's what I would do. Instead of having the sum case, I would simply, whoop, you see I'm being very strategic about how I erase here. Parens, handle, not bound, goes to this. And this is my working search EHS. Okay? Here's how you should think about it, right? Remember our contract. Our contract here, our precondition, our specification, is that search EHS, search whatever, should return raise not bound if it doesn't find the thing. So if I don't find it in the left, that is if I get the not bound, I'm going to go to search the right. It's the same as me casing on the return value, but now I give back information, not in terms of the value I return. Sometimes I give back information in terms of the exception I raise. So this exception not found is how I signal to my handler, my recursive call, hey, you didn't find it, go search the right. Okay? And now I don't have to deal with the sum nonsense because this guy, if there isn't an exception, it's just going to go to a value. And then this whole thing is going to go to a value, right? So this is how we would do this exceptional handling style, where instead of having my none case and casing on it explicitly, I just handle, okay? And that is one way to think about it. But and let me show you this thing also. So by contrast, I'm gonna flip a RAMA real fast and go between these really fast. Do you see sort of the differences here with the CPS version, which is in the CPS version, I add my continuations. Instead of raising not bound, I do my FC, my failure continuation. Instead of returning the value, I do SC, and then I add in this kind of like, I add in this success continuation, but I wrap the recursive call in a, I don't know why this prime is here. I wrap the recursive call in this failure continuation. And you see how, like, if you squint your eyes, like, they look pretty much the same? Yeah, similar idea, okay? So that's exception handling style. It's a bad idea. Don't do it. But you can, all right? And if I'm really cruel to you, I'll put it on an exam. Okay. The benefits being almost none. EHS is really hard to read. It's really hard to understand because when something raises an exception, it just goes out. It just goes, it goes, it goes, and it's never clear to you whether or not there's a handler. In terms of like this search EHS, like what happens if now my call to search EHS doesn't handle not found, then I crash. So the problem with exceptions is that you have to rely on discipline to handle the exceptional cases, but you don't have like a type level thing where like you have to handle the option, you have to handle the none case. Now it just relies on discipline. So exceptions again are akin to preconditions as options are to not preconditions, I guess. For a little SAT analogy for you. Okay. All right. And then yeah, I think this is again like me warning you again that like it's a nightmare to debug exceptions. Okay, like this idea of like non-local control flow, which is kind of like I can be here and I can be like miles down. I can be like safely here doing my little computations, and then I get an exception, and then I just go straight here. I just jump out of my context to go to the nearest handler. Is very, very dangerous. It's equivalent to a go-to, because a go-to just says quit what you're doing, stop, hammer time, go to the nearest handler. All right, do not pass go, do not collect $200. Same idea here with handle, right? So just be wary of that. All right. But it's really good for if you like already are in a failure case and you want to like print out some information and then crash. Okay. It's good usage for like error recovery. Like you're running your proxy server and then you get malformed data and you need to exit, so you raise it and then you print out some information and then you stop. Okay. But the idea is that like it's better when your exits are clear. That's kind of an aside. And then the last thing I kind of wanted to talk to you about is the fact that we can go really hard with this exceptional control flow idea, because before we were talking about search, which either returns a value or it raises an exception. I'm going to do one better for you. We're going to talk about a function which only raises exceptions, and that's how it returns data. So we're going to talk about this function called listMaxExn. Note the exn I put on it, but we have this. What is this? We have this exception max, which takes in information. I forgot to tell you this also. I guess exceptions can take in information the same way that you put this in a constructor. So this declares a constructor max that takes in an int, and it gives back an exn. So max is of type int to exn. Okay, so I can declare both of these exceptions here. The next one's going to be no max, all right? And this is going to be our promise. listMaxExn can either raise max m or raise no max, and nothing else. It will never return a value, so it has type alpha, because it never returns. But this is a fun way we can do listMax, right? So let's define it. So if I had listMax of exn, if I had nil, I would then want to raise no max, right? Because I don't find a maximum element because the list is empty. Otherwise, if I had listMaxExn, if I was trying to find the maximum element in a singleton, that would just be my singleton item, right? So I would raise max of, and I'm going to put parens to make it very clear, raise max of x, my only element. And in my recursive case, I have x cons x is our good friend. What am I going to do? Well, I kind of want a case on my output, but my output is an exception. So actually, let me just go ahead and do listMaxExn on x's, because why? I don't care, right? But if I ever get an exception from this, I can handle it. Because let's suppose that I have max. Like that means that this thing has some element inside of it. Okay? Well, if I have max of y, I would actually I'd re-raise because I have to, raise max of, suppose we have a max function that just like computes the max. I don't feel like doing the casing. x comma y. Does this make sense? Like if I get a maximum, if there is a maximum in the tail of the list, my true maximum is the max of those two things. It's the same as what you've already seen. But now I put it back in the exception. I package it back up. But there's also another case. What if this thing returns to me none? Sorry, not returns to me none. You think of it as returning to you none. It raises to me no max. Well, if I have no max in my tail, that is to say this is empty, I would say no max goes to raise max of x. Actually, sorry, this is redundant. I could have put this away, or I could have. So basically, the idea is that this second case or this case, these are optional. You have one or the other. If I didn't have this, I would do this. But because I have this, I don't actually need to do this. Sorry. I was thinking in my head, like, I know for a fact that that case was not actually on this slide. And I was thinking, why did I do it that way? And it's because it's the right way to do it. Yeah, OK. Kind of spooky. So do you see what's happening here? This function only ever raises max or no max. And if it raises max, it has that data, which means that any caller of list max exn can handle it to get the value out, or it can handle no max. So equivalently, actually let's go even further. Let me do the whole shebang with you, OK? We can go in between these two things, as I alluded to earlier, because I can just write my list max function. Let's call it list max opt L equals list max exn given L, and then this whole thing is going to handle. What's it going to handle? If I get no max, I'm going to give back none. And then if I get max of x, I'm going to get sum of x. We can define our regular optional type returning list max in terms of list max raising an exception. And actually, that's a pretty common practice, I'll say, if you want both versions. You define the exception handling or raising one first, and then you handle that to get the option. I mean, you don't define a function that only returns data via exceptions, OK? But if it did raise an exception, yeah. Any questions on this? Because this is kind of spooky. And there's really no reason why you should want to do this, like literally none. But it's kind of fun, I think. All right. That's list max ESN. All right. Last remarks here, which is that there's nothing inherently wrong with exceptions. They are go-tos, which means they are ugly. It means that they are unclear, they are undescriptive. You don't want to use them all the time, but there are use cases because you might want to do some error handling. You might want to just quickly write a function which can side effectively sort of get out of its context. It's okay to use them when the preconditions are very clear, but just be careful because sometimes your preconditions like this, right, are not like this, but sometimes your preconditions are worth raising the exception. Like as in, you know very well that it's not going to happen, so it's okay to write the exception raising version. But when it's less clear, then just expend an extra 2 or 3 lines. Write the function that returns the option, okay? Because an extra 2 or 3 lines of casing is going to save you pain later, all right? This is basically the same sort of idea as like null pointers, okay? It's like use the data that you want to do, right? Like don't put it into the data that you return, right? Don't rely on this exception stuff. It's a similar sort of idea, okay? Yeah, and I already told you about the error handling thing, but yeah. Exceptions are okay. Don't use them too much. A little bit of a downer ending to this lecture, I think. I'm 3 minutes early, but I don't really have much else to talk about. I'm waffling at this point. So please fill this out if you have time. It takes you 30 seconds. I will take questions about CPS.